is it real?
Shh. Wow, man. All right. Wow, voice is echoing funny. I want to talk some today about operating system security. Start talking about operating system security. So first, actually, I'm going to stop share. What is an operating system? Yes.
It's a layer of software on top of hardware computing systems that you allow a user to operate or to interact with the hardware.
It's a layer of software that allows the user to interact with hardware. Pretty close. Yeah, it's the operating system is generally meant to help manage the resources. It is an interface layer, helps the user interact with the system interact with other components in the system, helps it interact with the user. Often we think of it as a layer of abstraction. This is very common in computing, right? We've got the lowest level details and stuff, but that's too much to deal with. So we're going to abstract away and give you a simpler interface. You think about your car, right? My car, it's real simple. To start the engine, I push a button. That a lot more goes on under the hood, literally under the hood. A lot more goes on to get that engine going and that car running. I don't have to deal with it. The interface is simple. It keeps it going. When I want to drive, I push the gas, I turn the wheel, stuff like that. Again, the car, that's a simpler interface. So that's what operating systems are doing. What operating systems do we have out there? Windows. Linux. I'm sorry?
Mac OS.
Mac OS or iOS, which is actually a variant of Linux. BSD, Berkeley Standard Distribution, a version of Linux. Actually, a version of Unix. Let me be sure. Unix was the original one. Linux was supposed to be a free version of Unix because who was it? Berkeley generated Unix. Then I think it was Sun Microsystems bought it and then started licensing people. So then a whole bunch of people started doing free versions. This is an Android phone. So Android OS is a version of Linux. Xerox, that was a good one. Plan 9, that was one of my favorite ones. Ubuntu, version of Linux.
Temple OS.
You betcha.
What was that one?
Temple OS.
Temple OS. I'm not familiar with that one. There's lots of them out there. One I've used, RTEMS, which is a real-time executive for multiprocessing systems, and actually is not technically an operating system, just a collection of libraries, but they work together to kind of provide you the services. There's actually several different real-time operating systems out there that people use. What do I mean by real-time versus non-real-time, would you think?
Updated in real time or
So a real-time operating system is one where the tasks and processes and programs running on it have hard or soft real-time deadlines. So, I need it to respond within a certain number of seconds. I need it to, the power grid is going out and monitoring voltages on power lines on a regular basis, every few seconds or whatever the monitoring is. An airplane, when it's flying, I need to know my altitude, my wind speed now, not when it gets around to it, not after the latest update is being installed while I'm in the air. We don't do that. Now, but real-time operating systems have specific timeline constraints, deadlines. And so they're designed to allow those tasks and processes to be scheduled and to run and to meet those timing deadlines. Where a normal general purpose operating system like Windows, there is no such thing. As I could tell yesterday when I was editing the slides, and all of a sudden it would sit and spin for a couple minutes and not do anything before it started accessing it again. That's unacceptable in a real-time operating system. So there's lots of different ones out there, and they manage the resources of your systems. Yeah.
But doesn't Windows constantly monitor temperatures of like parts and stuff, or?
So does Windows monitor the temperature and stuff of your hardware?
Yeah.
There may be programs in there running under Windows that do. It's not Windows specifically itself that does that. Because it's very specific on the hardware. But that's an issue. So modern operating systems deal with lots of different hardware devices. And so we need programs to help us interact with those hardware devices. We typically call those device drivers, at least at the lowest level. They abstract away how you deal with the device, reading and writing values from that device into something more usable by the user. We deal with multiple programs running at the same time. We call them processes typically. How are they scheduled? How are they run? You know, older microprocessor will have one CPU core. It can run one thing at a time. A modern operating system is not running one thing at a time. You know, if I run, let's see if I can actually fire this up here. If I fire up Task Manager here, let's see if I can share. It's showing 4 different programs running right now. Well, that's not real. If I look at all the processes running on here, these are all the different processes or programs running under this Windows right now. That's a lot. Okay, this machine may have 4 processing cores, 4 CPUs. It can run 4 things at once. So it's got to swap between these. The operating system's in charge of that. Scheduling which one runs, running which one. Most of those are sitting there not doing anything until something happens. I'll have a keyboard driver. It responds when I hit a key on the keyboard. The video is running constantly because we got to deal with the video, but other things aren't. Each of these programs takes up a certain amount of memory. There's a fixed amount of memory in the machine. It's allocated out in chunks to the different programs. You get this piece, you get this piece. Now think security. Your program's running on my machine. You know, I download a program I got from your website, I put it on my machine. Do I want to protect? I want to protect my other programs from your machine, from your program. Accidental. If your code wasn't well written, it could be affecting my processes. I don't want that. Deliberately, I don't want it going out and messing up the code and the rest of my programs. And so operating systems are designed to handle that. Modern operating systems do a very good job of that. Old style ones don't. Some real-time operating systems remove those protections to make things faster for the system. Modern microprocessors do things to improve performance. And operating systems have to take that into consideration too. I think of an example of something called a cache. Now you've all heard of probably, oh, it has 16 megabyte cache or whatever, you've heard that word. When we're dealing with a computer system, we have RAM, our main memory, and then inside the microprocessor core, we have faster memory that is called a cache. And so when I want to read something from main memory, I copy it into the cache. And then I'm accessing and reading writing from the cache because that's 10 times faster than accessing the main memory. And then that actually is loaded, that data from the cache is usually loaded into registers, microprocessor registers, and you only have a few dozen of those. And that's really, really fast memory that the microprocessor uses. And most operations occur just on those registers. When it needs space, it uses the cache. When that needs space, it uses main memory. When that needs space, it uses the disk. And each of these is cheaper per megabyte as you go down, disk, but slower. The slower it is, the cheaper it is. When I'm loading my program and I'm switching from one process to another, the code for my program exists some in memory and has to load into cache. The data for my program has to load into cache. I now may switch to another process. If that process is not doing much and my cache is big enough, some of it could exist in the old cache and it could leave my stuff there. So when I switch back, mine's still in the cache and I'm fast. Real-time operating systems designers hate that Because they say, when I switch from process 1 to process 2, is process 2 in the cache or not? I don't know. If it's in the cache, it runs at a certain speed. If it's not, I have to wait for it to load, which slows it down. So by default, the real-time system operator, when we switch, we flush the cache, everything's out of it. And so we always know when we switch, we always have to load the code in, so we know how long it takes. Okay, there's a story, there's a model or moral behind this that I'm getting to. We used to have, when they were designing things for real-time systems like an airplane with slower processors, a collection of different microprocessors sharing a common data communication bus to process data. And they knew that if process 1 is running and sending data over here, nobody else should use it. And so they had ways of checking if it's being used and timing how long each process could use this. They then integrated stuff, and this was the Airbus, into a single microprocessor with multi-cores. Actually, this was single core processor, but it was fast. And they say, okay, we'll switch between tasks. So process 1 is running. Process 1 has a coding error. Process 1 says, I want to transfer a whole bunch of memory from from disk over to RAM. They use something called direct memory access, or DMA, so the CPU doesn't have to do it. It's a special piece of hardware, copy stuff right from disk to RAM. But they coded it wrong, so they're copying too much data. So it was using the system bus. Switches to the next process says, oh, I'm not here. I got to load my program from RAM into the cache. Oh, but the system bus is busy. I have to wait. Because the previous process had overprogrammed the system bus, and they didn't set in the timing to keep them separate. Really long story short, the plane dropped 10,000 feet before the pilots turned off the autopilot that was misconfigured and kept them from crashing. Because the process on the autopilot that was supposed to keep the plane afloat wouldn't run, couldn't check anything. That's a safety concern, but we have these same concerns in security, keeping things separated from each other. That's what operating systems need to do. That's what I'm going to be dealing with. There's a whole class about this, by the way, but we're going to cover this in a couple. Actually, there's 2 whole classes about this. 240 is how does operating systems actually work? And then I think it's 350 is the operating system security course. So it's a CS 240 and then Cyber 350. Right, so I already discussed all this stuff. It's a program works as an intermediary between the user application and the hardware. We talked about that. It manages the hardware resources. It provides an environment which a user can execute programs and software easily on a computer system. The nice thing about it is like file systems, right? I'm storing files. I don't need to know that that file is stored on a hard drive, on an optical disk, on a thumb drive, on all these different, physically different storage devices, because it abstracts it away. Now, modern operating systems are usually multi-processor and multi-user systems. And we want to isolate the users from each other. Now, it could be they don't run at the same time. My computer at home, multi-user, but you know, the family computer, my wife's logged in or I'm logged in, but we're not logged in. We're not sitting at the terminal using the computer at the same time. Other systems, if you log into the CS120 server, that's running multiple users simultaneously. And the operating systems need to deal with that. So they need to deal with permissions. What can you and can you not do? I should not be able to read and write your files. I should not be able to reformat the whole hard drive if I'm a standard user and there's a bunch of other users on the system. I should be able to read and write my own files, copy and delete them. I should be able to send things to the printer. You know, but maybe I can't install new software. Maybe that's not permitted for me. So these are things that the modern operating systems have to deal with. So in general, a user executes a program. A program usually consists of what we call one process. That process is assigned system resources. Memory the program can use, the state, what the program is doing at the current point in time. So what are the values in these computer registers, the program counter, what line of code is it on? Stack pointer keeps track of where it was in the depth of code. Don't worry about this if you don't know what this is. Access devices, communication, processes can create other processes. And the operating system keeps track of all of this using what they call a process table, keep track of all the processes. What I was showing you earlier when I did the task manager was a list of processes. That's a graphical representation of the process table. And it switches control back and forth between the processes. What I mean control is which process is currently using the CPU. It allocates, deallocates, reallocate resources each time a different process is activated. Now, a process can consist of one or more threads of execution. So a thread is like a mini process. They share the same code, they're sharing the same data, but this is very common. I'll have a thread sitting there waiting for user input on a keyboard or mouse. Another one dealing with, if I'm playing a game, threads dealing with what the non-player characters on the screen are doing. Another one dealing with displaying the graphics. Another thread dealing with their separate independent tasks that we're doing. So they can execute concurrently. And if you have a multi-processor system, multi-core system, they can execute in parallel. And so all these different things happen. Modern video cards actually have a graphic processing unit, a GPU. It's a separate microprocessor with the ability to run lots of threads. And you'll say, okay, you deal with this part of the screen, this part of the screen, this part of the screen, or you deal with this image on the screen and this part, and something else now merges them together and make sure they overlap correctly. And you can have hundreds or thousands of these mini threads running in the GPUs. Usually running very, very simple calculations compared to what the whole processor is doing. So you've got to think about this in context. There's a lot going on. The operating system manages it for you. The operating system can mess up for you too. So in general, we'll have, at the bottom, the computer hardware. Let's see. We'll have the operating system sitting on top of that, and the system and application programs. And the operating system may do a certain thing, and then a system program is a utility that makes life a little easier. The user interface, when I'm logged in, the graphical user interface, the desktop display is a system program, and that's not the operating system. In Windows, it's Explorer, desktop. I don't know if they call it Desktop Explorer, but it's Computer Explorer, whatever. It's Explorer that is showing you what's on there and displaying it for you. It's a system application. And then on top, you got the users. Whoops. So I brought this up already, but let's ask, what if there's multiple users sharing an operating system, what needs to be protected? I'm actually asking this as a question. What do you think needs to be protected?
Each user's individual files.
Users' files. Got it?
System files.
System files. You don't want the user to reprogram the operating system.
Preferences?
Preferences?
Yeah, like what they set.
Okay, so the user's configuration data and settings and stuff. What's my default browser?
Privileges like one user has over others, like admin versus like general user.
Yeah, so this detailed on the system files, what are the privileges? What are the access? What user has what permissions? The operating system controls that, not the user. And so that's a system file the operating system has to keep track of. The devices themselves, the memory, the hard drive. Yes, I'm protecting you're protecting the files. I can go into the raw hard drive and read and write the individual sectors of the hard drive and decode it and figure out what your files are. That's not good. Or overwrite it. That's not good. And so the protections provided by the operating system protect different users' data. Read, write, execute permission, create permission, delete permission, copy permissions, those types of things occur. We'll talk about some of those as we move on. So memory, the RAM, the hard drive, the disk space, that all needs to be protected. Shareable input-output devices, such as disks, such as the keyboard, the mouse, the printer, have to be network, the internet. Well, if multiple people are using the network at the same time, how is it separated? Now, there's different types of shareable devices that you have to be aware of. And I should show this in a diagram. I probably should. Let me see if I can do this without my glasses. Wish me luck. Okay, so I'm going to say, let's have a square, right? A grid. So we'll have shareable devices and non-shareable things. What do I mean by shareable? More than one user can use it versus non-shareable. Only one user can use it. We have things that we'll say are P for preemptible or non-preemptible, right? So maybe a printer is a shareable device. Wow, this mouse is moving slow. We'll just call this print, but non-preemptible. What does preemptible mean? Is you're using it, I step and say, my turn. Now, I should not be able to do that in the middle of printing your page and start printing my page and then go back and you preempt me. We will take turns. That's kind of what I consider a time shared IO device. You have it for a certain amount of time than I do. Preemptible, the CPU. I'm running for a certain amount of time, but the system can stop my program at any point in time and start running yours. Other things like maybe there's something in disk. My file is on disk. You can't cut into it and erase it and delete it and use it. And we're not sharing a disk file. So maybe that, or is that shareable? So we got to think about that one, you know, and so we just think about the resources and how they're dealt with. But again, the important thing is some are immediately preemptible, some aren't. Some you get for a certain amount of time. Now that broke that DMA device thing I was telling you about on the airplane. That wasn't preemptible. The bus wasn't preemptible. We couldn't say, hey, stop this guy using it, it's my turn. And it should have been. Now, the interesting thing is the old system, it was preemptible. They had a hardware interlock. You say, hey, my turn to use the bus, stop them for now, let me use it and then give it back to them. The new system, they said, oh, we got software dealing with it, so we don't have to have this extra hardware protecting us. Where before it was actually hardwired. You have it for this amount of time, click. Now you have it for this amount of time and yours is turned off. But now that we have software, we don't need hardware protections because software never breaks. And I say that because the Therac 25 irradiation machine killed people with overdose radiation because they removed hardware interlocks with a new software interface because software never breaks. The Ariane 5 rocket crashed. Actually, they had to blow it up before it hit Paris because software, they changed, when they went from Ariane 4 to Ariane 5, they changed the hardware, but they were trusting the software to take care of the changes because software never breaks. Only hardware breaks, so we don't have to do this. And I can go on and on. There's lots and lots of examples of things that broke because somebody assumes software doesn't break. Software doesn't wear out. The other thing, and I was involved in this, we stopped this one. This did not happen. There are, for nuclear reactors, there's the ability to drop control rods into the reactant chamber to stop the reaction from going. There's devices that measure what's happening. And it's like if you have too much temperature, too much pressure, too much neutrino flux, whatever, you're having a runaway reaction, you drop the control rods to stop it. The requirement is each of the devices measuring this are independent. You have multiple devices in case one fails, you've got backups. They do the math on the failure. Oh, the likelihood of this is failure is, 10 to the minus 5. We'll have 3 of these together. So maybe it's 10 to the minus 9, like, 1 out of a billion chance it'll fail. We're good. They wanted to replace those hardware systems with software systems. And they said, well, we're doing the same math because we're just replacing like for like. And a bunch of us, and this was in the 90s, were like, no, that doesn't work this way. Hardware failures are usually independent. When this device fails, it doesn't mean that device failed at the same time because it wore out. Software failures occur when the environment hits a certain set of values and the software wasn't coded correctly. Well, you guys are all seeing the exact same values from the environment. Your software is going to crash at all the exact same time. It's not independent. It wasn't the hardware failure, it was a software failure, and you lost the independence. So we did that for INL, wrote a report, and they didn't implement this. So yay. That's why I learned about the Theractic 95 radiation machine and several other things too. Our actual programs themselves need to be protected. Think about it, you know, malware comes in, malicious software, a virus, and it infects my program. That's not good. My operating system should protect me. Obviously it doesn't, or we wouldn't have viruses. The networks, the files, all these things need to be protected. And you're seeing all this and you're thinking, isn't that a lot of work? Isn't this hard? And the answer is yes. It's job security for all of you. Okay, so what does an ordinary operating system provide you? The authentication of users. Hey, remember that term from way back? Before somebody logs in and starts using the system, you want to authenticate who they are. It provides protection of memory. So my process running does not adversely impact your process that's running. Just think about RAM in terms of that. File and input-output device access control. Each user has different permissions to the files. The standard operating system controls that. It allows me to say, yes, you have access. He doesn't, she does, he doesn't. Allocation and access control to general objects in the system. So it could be databases or other more abstract concepts in the system. Enforcement of sharing. Hey, maybe I want to share a file. It allows me to share, but allows me to share with whom I want to. Guarantee of fair service. Hey, if we have multiple processes running on the system, multiple users running on the system, do they get fair access to the CPU? Fair access to the network, fair access to the file system, etc. Inter-process communication and synchronization. Typically, when you have programs running, they need to, some of them need to communicate with each other, or processes running. Think about it as my program, Microsoft Word, needs to interact with the file system, the device file system driver. Actually, it interacts, I'm using OneDrive, so it's interacting with the OneDrive program to store my file on OneDrive. You know, that's a simple example, but you know, typically this needs to be dealt with. And synchronization. When think about a banking example. Okay, I want to withdraw money from the bank. I think I've used this example before. So I go to the ATM. I want to withdraw $100. The ATM is synchronizing with the main server, communicating with it, saying, what's the bank account? Let's withdraw the amount. Let's dispense the money. Let's update that. If anything goes wrong in that step, I want the final balance to be correct. If my money didn't get dispensed from the machine, I want my bank account to reflect I didn't get any money. The bank wants to know if the money was dispensed from the machine, then my bank account, my balance wasn't, you know, reduced, that I got the money. We have to synchronize and make sure that these things that are happening on different machines coordinate with each other, or in different processes, or different threads within a process. There's a very simple concept, a data structure called a stack. Okay, just think of it as stacking things one on top of another. And when you want to get something off the stack, you take it off the top. Push something onto the stack. So it's a storage way of storing and organizing data. If I have two threads accessing a stack, one goes and says, hey, get me the top thing from the stack. I'm going to change it. I'm going to delete it. The next thread says, give me the next thing from the stack. Well, if they're both trying to get it at the same time, are they both operating on the same thing? Does one get it first? Usually the operation to remove something, grab the top thing from the stack and remove it is a couple different instructions. If in the middle of what I'm doing, another instruction another process interrupts me and starts doing things, we get problems. Operating systems are good at that. You'll hear that about CS240. There's a lot of discussion about that. Protection of the operating system alone protected data. The password file, the user information file, the operating system configuration stuff, the permissions, all that needs to be protected. That's all part of ordinary operating systems. We also have a concept called a trusted operating system. A trusted operating system is more secure than a general purpose operating system. It has additional security features, usually from the point of view of the US government or the government agencies that use trusted operating systems. These have also been reviewed and evaluated. There's a, going back to the 1980s, I think it was 85, the US government put together a document called the Trusted Computer System Evaluation Criteria. They published it in a pamphlet that had an orange cover. So everybody called it the Orange Book. And it talked about trusted operating systems and how you evaluate them to make sure they're secure and they do everything you want. And they had level A, B, C, and D systems. Level A being the absolute most secure, B being pretty good, C being commercial, and D being, well, forget it. D was you submitted the system for evaluation, but nothing else happened. Then they had a network interpretation of this because the Orange Book was just for single computer systems. They want network interpretation, so that was the red book. Then they had an authentication guide. I believe that was the blue book. No, that was the yellow book, and then the blue was something else. They had a whole series of these, and we ended up calling it the Rainbow Series. You Google NSA's Rainbow Series, it's all out there publicly available. Later in the 90s, they came up with a different way of doing this called the Common Criteria, where they merged NSA's Rainbow Series with European Union's Green Book series with some others to try and get that together. Now they're doing completely different things for evaluation. The standards are out there, but they talk about making sure the systems are designed correctly and have certain extra features that a standard operating system doesn't. So better identification, authentication, something called mandatory access control. And we'll talk about this more in detail, but in a traditional operating system, I could say, let Dr. Soul read my files, and he'll be able to read my files. I could say Dr. Song can't, and she can't. Mandatory access control says, I don't care, Jim Oswald, you have a secret level clearance. You cannot share these files with somebody who doesn't have a secret level clearance, but has a lower level clearance, like confidential. Or this is a top secret file. You can't share that with somebody else. Or no, Jim Oswald, you don't have a top secret clearance. Nobody can share this top secret file with you. It is mandatory. It's based on the security policy of the organization that this cannot be shared, or this can only be shared this way. And the operating systems enforce that no matter what the user's discretion is, their discretionary access control. Talk about it. Object reuse protection. Okay, I've got memory. I've got stuff on my hard drive. I got stuff in the RAM. I'm done using it. I delete my file. Most operating systems, traditional operating systems, when you delete a file, what it does is says, I'm no longer using this part of the disk, but doesn't go out and erase anything, doesn't change it to a bunch of zeros, just leaves it sitting there, marks its table and say, this is now free for use. So the next person who goes out and allocates space or who gets that space on the disk, if they don't say overwrite it, they can now read what you had in there. Same happens in RAM. Okay, object reuse protection is no, you're going to zero that out because that could have been top secret data in there. And I don't want somebody else, that could have been your encryption key or decryption key and somebody else can read it. I don't want that there. Complete mediation, all access is controlled by the operating system. Trusted path. When I log into a system, how does it know I am at the keyboard and not remotely logging in? Because often you can remotely log into a system and the system thinks like you're at a keyboard. A trusted path says I'm physically at the keyboard. For those who've used Windows systems, Control-Alt-Delete is a trusted path. It's a hardware-based thing. You hit Control-Alt-Delete, the hardware knows about it. Now, we found ways around that, unfortunately, because Windows isn't a trusted operating system. But that was designed to be hardware triggers that. And the operating system doesn't even see it initially. The full accountability and audit capabilities. Audit log reduction, because if I'm auditing everything you're doing, it's huge. Is there a way to reduce it so I can actually see what's going on in the system? And intrusion detection built in. So we got our normal operating systems, we got the trusted ones. Trusted operating systems are also designed in a specific way. They use what we call a kernelized design. A kernelized design is minimalized code. You don't put everything inside. So what we have is what we call our trusted computing base. The portion of code that's responsible for enforcing security. That should be as small as possible. So there's a SEL4 operating system developed in Australia. It's a trusted operating system. Their kernelized design. They have under 10,000 lines of code in this kernel. And it took 75 man years to evaluate it in terms of effort. I shouldn't say man years, but person years. And millions of dollars. It was quite expensive. Windows NT, let's see, Windows NT, I think it was, version 4. I got a copy of that source code back in the late 90s as part of a project we were doing for Microsoft. 3 million lines of code. Very different than 10,000. Nobody can analyze 3 million lines of code. Now, that's not the core operating system. That was all the device drivers and everything else. But still, there's millions of lines of code in the core Windows operating system. It trusted, you're gonna have much less. Separation, we want isolation between the different users, the different processes, the different aspects. Full controlled separation. Modifiability. Controls over how it can be modified. Compactness. We actually have, do I have that in here? Yes. We call a good system neat if the reference monitor, the part of the system that enforces security, is non-bypassable, means no, but, and let me actually do this in a different order. Always invoked. I want to read a file, it checks my permissions. I want to write to a file, it checks my permissions. That's always invoked. Now, I've had arguments with people in the community. Okay, it's always invoked, so why are you worried about non-bypassable? Always invoked means when I ask the operating system to read and write a file, it checks my permissions. Non-bypassable says I can't go to the operating system, says give me access to the raw hard drive. Don't treat it as a file system, treat it as a separate device, and I'll read and write everything there, bypassing the file system controls. So everything is encapsulated, everything is controlled, we have that. It's tamper-proof. You can't go and the system protects itself. I can't go and modify the file system permissions. And it's evaluatable. It's small enough to understand and use. Now, evaluatable, NSA was saying at the time the NEAT acronym was developed. I mean, these terms are from the 70s, but the NEAT acronym and the use of that was more in the early 2000s. They were saying under 10,000 lines of code because they figured it took a person year to handle 1,000 lines of code. The trusted computing base mentions a collection of system components necessary to enforce security policy. The larger it is, the harder it is to evaluate. Take things out of the kernel. If they don't have to have full access to the system, don't give them to that. Now, this is hard. We have market forces that push us the other way. So in the 90s, Windows 3, had the ability for a graphical display of games inside separate windows. And they had a whole layered approach to this, and you wanted to draw sprites or other things. They had a mechanism for doing that. The problem is it was too slow because it was going through layers of checks and permissions. And there was a game designer said, our game cannot run on Windows because you're not giving us access to the raw hardware. Let us have control of the raw device hardware. And Microsoft said, yeah, we want your game to run on our software because that helps us with market share. We will do that. And so the device drivers and graphics drivers moved into the kernel, became part of the trusted computing base. Much more of it did than it should have. And we see this throughout history with systems. Some it's just accidental design, some it's deliberate. Yes.
You said it was much more in the kernel than it should have been. Did that like end up affecting anything?
I'm sorry.
You said that it was like much more built into the kernel than it should have been. Like, what did that end up like affecting anything? Like,
Yeah, it opened up some huge security holes.
ah,
I think back to when I started doing security work. The original email program that we were using in the Unix systems, or email receiving program. So think about this for a second. I have a multi-user system. I receive an email. I want to put that email in that person's mailbox. Now, this is all before things are stored in the cloud. So they're stored in the individual system. So we set up a mailbox for every user. Mail comes in and it's appended to their mailbox. That means the send mail program, the one that was receiving all this stuff, had to have permission to write to everybody's mailbox. Well, each user has different permissions, so they gave this root access. Email, which means it had access to everything in the system. Email should not have access to everything in the system, but it was the easiest way to design it. Robert Morris Jr. took advantage of that in the late 80s with the Morris worm that shut down the internet for a couple of days, the whole internet. Because they also had a built-in debug feature in the SendMail program, which they hadn't disabled. So the debug feature was, oh, when you enable this, when you receive this email with the debug feature, download this program and execute it. No checking. And it ran as root, had full permissions, and that program then downloaded his whole worm and had to do a whole bunch of other nasty things. Well, nobody would use the debug feature unless they were trying to debug the system, right? And when we need root, now email doesn't need root. We found ways around that. Separate isolation, separation. Our trusted computing base, though, must at least manage process activation. How do you fire up a program and get it running? Execution domain switching. How do you switch between programs? The trusted computing base has to do that. We can't keep that up there. Protecting memory, protecting IO operations. At a minimum, it should do this. Now, some people say it should do the identification and authentication. Some people say it should do the logging. Other people say, no, it just has to enable the logging program to run and protect it from other things. It has to enable the authentication and identification program to run and protect from other things. And so there's this push and pull in the designs. And this has been going back to the original Anderson report, which is 1974, where they talked about the trusted computing base. So we've been thinking about this for decades. We're not getting it right yet, but we're thinking about it. All right, so in a modern operating system, what security features do we have? I talked about some of these already. We have user authentication, memory protection, controlling the interface to hardware, allocation of objects, access control to the objects, the file, and the IO, and protection of operating system data and code. Somehow, I don't know why I have this twice. So access control. Hey, we talked about this early on in the chapters. See, there was a trick. Subjects are permitted to access an object in a particular mode, read mode, write mode, append, you know. That's what we talk about access control. Audit is a log of which subject accessed which object, and that is maintained. Now, some audit logs are very simple. Who logged in? That's all we do. Maybe somebody creating a file or deleting a file, but we may not even keep track of who was the last one to access a file. Now, we do keep track of when the last time a file was accessed, because if you look at the information about a file, you can see last modified time. Usually it's date created and who created it is in there. And then last modified, but doesn't even keep track of who last modified it. Or worse yet, and what I prefer, all the people who modified it. Was there a question? Okay. Separation, how do we separate users from each other? We can do this by space, time, access control, or cryptography. So space separation, your stuff is on this hard drive, mine's on that hard drive. That's completely separated. We can isolate things and allocate the chunks. We can do it by time. There is, and this was years ago, but I think they still do this. I know at Idaho National Lab, they had a secure computing facility. People would bring in their hard drive, reserve the room for this time, plug that hard drive in. They now had access to the computer running on their device. When they're done, they pop that drive out and the system was reset. Complete time separation of who was using the system when. It was a very special purpose system, so you couldn't, not a bunch of people had a lot of access to it. Or cryptography, hey, my data is stored next to your data on the same hard drive, but it's encrypted with my encryption key. You can't see it. Or we just use access control. Most people do the access control with some space separation. Space separation also, you could think of, hey, this room, that room, different physical locations of the computers if you want. Virtualization, we'll come back to this, is another modern feature provided by operating systems, providing a simulated hardware environment. And we also have hardware protection of memory. And I'm going to spend some more time talking about some of these because they're important concepts to just kind of understand. I don't expect you to be able to implement them. That'll be CS240. No. But you should understand what they do and how they work. And a lot of them come out in the research, in terms of publications, in terms of just terminology. You'll see things like, oh, it has ASLR. What's ASLR? Object space layout randomization. Well, what does that even mean? And we'll talk about that. So with virtualization, the operating system presents each user with just the resources the user needs. So I can run a virtual machine. I was using one yesterday on one of the servers we have. The server has 80 physical CPU cores. This virtual machine is only about 20 of them. That server had 1 terabyte of RAM. This machine was allowed 125 gigabytes of RAM. Still not bad. And I didn't need it all for what I was doing. Disk space, allocates to disk space. So when I log in, I see a full desktop as if I'm logged into a regular desktop, though it's all over the web. The thing I showed the game and the thing the other day, right? The C2 games interface, that was a virtual machine running on another server, and I was seeing the desktop display of that machine. That virtual machine is really running using hardware control features and operating system control features that completely isolates me from other virtual machines in the system, if it's done right. Cloud computing, it does this a lot. So you fire up a virtual machine, it says, hey, I'm running, you've got this many CPU cores, you got this much of the RAM, you're doing things with this much network interface, and it's completely isolated from other virtual machines, just virtual machine, I don't know what else to call them. Other, instances of operating systems running that other users could be using. Okay, so a virtual machine monitor or hypervisor is the software that implements a VM. A hypervisor is very, very low level operating system software that gives you access to that hardware and nothing else. Now, you need certain hardware to do this. You have to have the ability to completely isolate people. Every instruction that microprocessor can execute has to be isolatable. I do know that Cynthia Irvine at the Naval Postgraduate School did a study back in the late 90s looking at everything, every instruction in the Intel microprocessor, or maybe early 2000s. And our Dr. Song followed up on that and looked at more recent instructions, the extra 500 they added over the decade since Cynthia Irvine did this. Which ones are virtualizable? Which ones, if you execute this inside a virtual machine, will not affect another virtual machine? Cynthia Irvine found several of these that have had problems. We found two. But of those several that would have problems, she actually informed Intel of this. And in their more recent microprocessors, they addressed all that so that these are truly virtualizable. These things would no longer cause problems. Now, sometimes what happens is a virtual machine monitor says, oh, wait, or the hypervisor, you're trying to execute that special instruction. We're not gonna let you. We're gonna simulate it in a way that keeps it protected. That really slows things down. Normally, it just allows you to execute the raw instructions on the raw hardware, what we call bare metal. Now, what's interesting is because of this virtualization technology, we can do things where I could actually, using the simulation technology, pretend I'm running an ARM microprocessor when I'm running really an Intel. And it's slower, but we have that ability now. QEMU is a virtual machine monitor that allows you to do that. You can simulate lots of different architectures and run things at different speeds. And isolated. It's great for experimentation. I love using virtual machines when I do cybersecurity research. I can have a virtual machine and visit a website I don't trust, and they can download and trying to infect my machine, and I can delete the virtual machine. I'm no longer infected. And it never gets to the core hardware, never affects the BIOS because all that's good, as long as my hypervisor is secure. There have been a couple of cases where people have done jailbreaks and gotten out of the hypervisors. We think we fixed all those. So, basically my concern is I want to ensure the program running within a guest operating system. So a little more terminology here. My main machine is my host operating system. If I'm running virtual machines inside that, each of those is running a guest operating system. So on my machine in my office, I have my host operating system is Windows 10. My virtual machines are running Linux, or Windows 10, or Windows 7, or Windows XP, or whatever I want to run. I want to make sure that the program's running within the guest only access the resources allocated to it. Now, I can have the VMs share part of the hard drive. I abstract that away and I do that. I say, hey, this directory in the hard drive is shareable between VMs. This way I can copy data between the VMs. It makes life easier. I can enable cut and pasting where I cut and paste in one window, from a VM and pay to another, or I could turn that off and say, you can't do that. So we have to ask, is it possible unauthorized parties to access the image or screenshot of the VM? So this is another thing. When I pause the VM and it's saved in a data file on my host machine, here's a copy of what you were doing. Here's your copy of that virtual hard drive and that virtual memory, and I can restart it. Well, it's sitting there. Can somebody else access it from another VM or from the main machine? How about the screen? The screen displays usually in VMs or remote. They're just graphical displays in a browser window, for example. Can somebody else see what that is? Maybe they can get my data. So we have to think about these extra security features now that we're virtualizing stuff. How do I secure the VM monitor or the hypervisor itself so somebody doesn't tamper with that and change things? So one thing I was doing yesterday, I was trying to help a student. We have a shared hard drive image that multiple VMs can access. So I set it up as read-only. Well, then I had to update it, and that caused a whole lot of problems because it was read-only. But so I had to go into the hypervisor, change the permissions, go in and fix things. And then reboot the student's machine, didn't realize she was using it at the time because I had completely separate access to this VM. Then she didn't see her. She was upset about that. Never let a faculty member be a system administrator. All right, what else? So separation. I talked a little about VMs. Separation, when we want to do separation between processes, between one VM and another, between a process in a VM and another process in my main machine and another. Again, like I said, it can be supported by space-time access control cryptography. Space, use different physical resources by different users. That's the easy way. Easy to implement, expensive, because every one of us needs a copy of that device. Separate by time. Execute different users' programs at different times. Easy to implement, but time consuming, and we got to wait for each other. The old timeshare systems did this. Back in the day, and this predates me, your program would be on a bunch of punch cards. And you would schedule a time to run it in the server and they would run it in. Of course, if you had a typo, an error, your program would crash, you get a message back saying it crashed and you have to resubmit the next night. They ran these nightly jobs. Yeah, that worked, but we don't want to do that anymore. Separation by access control. You know, this is applied to the objects maintained from the operating system. Who has read permission, who has write permission? And is this accurate? And again, separation by cryptography. That is complex and you have to hold key management. And one issue that comes with this is, what if I lose my encryption key? How do I get my data back if I've lost my encryption key? And it's happened to me. We had for a research project we did 15 years ago, we encrypted everything. And I found that encrypted file 5 years ago and thought, oh, I had that other stuff in there I should look for, but I couldn't remember the decryption key by then. It had been 10 years. I didn't absolutely need it, it just would have been nice. So let's talk about memory separation. Yeah, make sure that clock's right. This becomes a really important thing to understand. This is key to the way modern operating systems work. If I look at a 32-bit microprocessor, each memory address, part of the RAM, is accessed using those 32 bits. 32 bits define a single byte in the memory. 32 bits is 4 billion or 4 gig. That's how many unique addresses we can have. If I write them in hex, I can write it out. Each of these represents a single 4-bit value. 4 bits is 16 values. So we have the 16 values from 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 of them. A, B, C, D, E, F. Those are the other 6. So you get those 6 values or 16 values. So each of these is 4 bits. 1, 2, 3, 4, 5, 6, 7, 8 of these. 8 times 4. 32, so I have 32 bits represented by this 16 bits. Common way to write these. If I have memory in the system, typically I will lay it out starting at 0 here up to the highest memory. Some people draw this opposite direction, so be careful. Some people do it left to right. Normally you'd have low memory at the bottom, high memory at the top. Typical like Windows operating system, when a program is running, old school, let's go old school first, actually MS-DOS, and we didn't have 32 or 4 gigabytes of memory back then, 1 meg. Everybody had access to all the memory and the same memory. So that when I ran a program, I had to tell it start at this memory location, start at this other memory location. I couldn't, and it was really hard to run 2 programs at once, especially if they wanted to start at the same memory location. So we came up with the idea, researchers came up with the idea of virtualization of memory, which the idea is in the microprocessor, when I tell it access address, let's pick this one, C0000000, it goes to the hardware and the hardware says, okay, the user's asking for this address. What is the real address in memory for that? And it translates it to that real address. And I'll go over that later, how that actually works. I think CS150 talks about that some. 240, we'll talk about it more. So each program, sees memory the same way from the whole 4 gigabytes. They think they have the whole 4 gigabytes. Programs are usually organized where maybe the top gigabyte is reserved for access to kernel space, operating system kernel space. This is special reserved memory. Normal programs can't access it directly. We just say, set it off, you're never going to touch it. Let's go to the bottom here. There's usually some stuff at the bottom that's very specialized for accessing the operating system from your program. I'm not going to worry about that. What gets important here is now the text. This is the actual executable code. Your binary code, your executable program, it's loaded into memory. And here's an example. On a 32-bit processor running Linux with GCC compiler, the default address, start address is 08048,000. Don't ask me why. I could explain it, but anyway. That fills up a certain amount of memory. Your program, when it runs, is compiled to assume it starts at that address. When you have to have jumps to other addresses or calls to other functions, it knows where those addresses are because they're somewhere here in this memory. Then there's portions of your program that are data values that are static, that never change in the program, like strings, prompts. Please enter your password, username, all those things that never change in the program. Help menus and stuff. That is stored in this read-only data section, right on top of your program. This whole section is read-only. The operating system protects it, and this part is the executable part. On top of that is what we call the BSS section. This is a section of pre-reserved memory. Your program says, hey, I'm going to need this much space to do things, but I don't know what those data values are yet. They're not hard-coded. So we'll start this whole section, and it'll be all zeroed out. And it's just pre-reserved space. On top of that is what we call the heap. The heap is when your program's running and says, oh, I need more space. I hadn't reallocated this yet, but I need to do it. Give me, an extra megabyte of space. And so the operating system or the runtime support system goes into the heap and says, sure, I will. Program called malloc or function call called malloc, system program allocates malloc space for you, memory allocation. When my program is running, and again, for those who haven't written code yet, this is hard to understand. If I call another function, I usually pass information to that function. Now I want to call the square root function, I pass it the value I want to calculate the square root on. How that is passed is it's old school. It's stored in a location of memory called the stack. Remember I talked about stacks? And then the function, the program that's called can look on the stack and find it. When one function calls another, it also says, pushes on the stack, hey, this is where I was. This is the next instruction you should execute when you return from the called function. And that's stored on the stack. When my function is called, I may need extra working space, extra places to store values, variables X and Y. They need to store something when I calculate things. Those are stored on the stack. And so I push things on the stack to make space. When I'm done, I pop them back off. Now you notice I'm pushing, I'm going down, I'm popping, going that because stacks are upside down in the way we do modern systems. And when you push on a stack, it goes down in memory. So that goes this way. And when you pop, you go back up, which is opposite. The stack's hanging upside down, but who cares? What I care is if I've allocated a local buffer to store user input, hey, I'm going to create 80 character space for 80 characters. I'm going to ask you to enter your name, 80 characters. That's fine. Nobody's name's that long, right? You enter 120 characters. I don't check it. My system starts reading. It goes right up way past your buffer, overwriting the return address I had stored there. And so now when I return this from this function extra name, you force my program to go run somewhere else. And if you're clever about it, you get me to do a whole bunch of nasty things that I didn't want my program to do. Common problem. We've known about this problem since the 60s. It still is one of the most common problems, programming problems, because you guys, when you write code, don't check to make sure the buffers aren't overflowed. Me too, but no, I think I do that in all my code nowadays. Okay, but this is a common way of understanding. You'll hear about stack overflows, heap overflows. You'll hear about things like that. That's what this all deals with in our typical program memory layout. So we're going to think about this. I'm going to come back to this when we talk about how we actually organize it and do protections of these things. And there's lots of different options people have, some of which are still implemented, some aren't. And then later when we get to programming, we'll come back to this part, this buffer overflow problem, because that gets really cool. All right, I'm out of time, so.